So in this lecture we will see a little bit of the ideas behind the 3D reconstruction methods. I have borrowed many of these slides from a more mathematical oriented presentation, but I will not get into the mathematics in this time. So let's see some of the ideas. So tomography is about reconstructing a 3D object from its projections. And the projections is something that we collect at the microscope. So when we project in this direction, what we see is the superposition of the cylinder and the sphere, and that is what we collect in the 2D image. Another way of getting to the images from this 3D object is by slicing. This is normally what is done when presenting a volume, so not when acquiring images from a volume. So when we reconstruct a volume and we want to present it, what we can do is just to cut a slice through this 3D object. And so the cylinder and the sphere, they are visible in different slices. So this is what we do when for instance we have this 3D object and we have a 3D surface representation of it, and then we make slices through different axes to have this top view, this side view, and this view from the back. Okay, so when we may also take the same object and present all the consecutive slices. So we would see for a head, we would see these ones, and this is exactly what we do when we are presenting a volume in CryoEM. And looking at the volume in 3D through the slices, I would say this is the first step towards recognizing artifacts in the 3D reconstruction, because very often you see strikes or stripes outside the object of interest. That is a signal of we call it overfitting. Overfitting is model bias in CryoEM, but you have aligned your images in such a way that these stripes are reinforced, and that is a mistake. Okay, so let's see what is the tomographic problem. So the microscope had an object inside, or infinitely many objects of the same size, of the same shape, and then it has generated projections. And then computationally, we have to take those projections and place them back into the 3D object. So the microscope is going from 3D to 2D, collapsing all the 3D information into 2D images, and we have to uncollapse those that information into a 3D object, and that is why the tomographic reconstruction is said to be an inverse problem, because from measures of an object, and measures are these 2D images, we have to reconstruct the object. And weighted per projection was one of the first algorithms to invert this process. So let's say that we have an object and we know that projecting from bottom to top, we have this projection, and projecting along this direction, we have this projection, and projecting horizontally, we have this projection. So one possibility to find an object that is compatible with these three projections is just to take the height of this projection. So let's say that this is 1 or 1.5 in these scale units, whatever they are. And since we know that this 1.5 is the addition of all these pixels, so we count the number of pixels. So let's say we have 100 pixels. So we put 0.15 in each one of the pixels, so that 0.0 15 in each one of the pixels, so that when we sum the 100 pixels, we get the 1.5 that we had at this location. And so this process of taking the 1.5 and smearing the 1.5 along the volume is called back projection. And we could do the back projection of all the other projections that we have. And with only 3, this object is compatible with these 3 measurements. There are many objects that are also compatible with these 3 objects. Actually, if we have, for instance, this object, and we generate many projections, we would be able to recover the object that originated them. But otherwise, if we only have 3 projections, then we see that this object and this other object both are compatible with our measurements, and we cannot say which one of the 2 is more plausible unless we have some a priori knowledge, like, okay, my object is concentrated towards the center, so these stripes coming out shouldn't be present. So that would be a priori knowledge that we might have about our object. And here you have the same process. So you have the reconstruction. If we have 2 projections, 4 projections, 8 projections, 16 projections, 64 projections, and 64 projections that have not been filtered. And we will see why do you need a filter for making this back projection. Okay, so the reason for the filter is coming from the central slice theorem. So the central slice theorem, when stated in 2D, is that if we have a 2D object and we have the Fourier transform of that 2D object, and we make a projection, a 1D projection of that object, then the 1D Fourier transform of the projection will be one of the lines of the 2D Fourier transform of the object. So by making projection and transforming, we find the Fourier transform of one line. So this is expressed in 2D and 1D, but the same idea applies to 3D and 2D. So when we have many projections, so here we are representing just one of them, we know that the Fourier transform of this projection will be one of the lines. And since we have many other projections, we have many other lines. And all these lines, they all intersect at the origin of the 2D Fourier space. And what we see is that the density of points towards the center of the space is much denser. So as you go away from the origin, the samples, the samples coming from the 1D Fourier transform, they become more and more sparse. So there are more space between one sample and the next. So the fact that these samples at low frequency, they are more closer to each other, that implies that the low frequencies are overweighted, and that is why we have, if we don't apply any filter, then that is why we have a low frequency component that is superposed to the original object. So in this unfiltered version of the weighted back projection, the low frequencies have been overstated, and the solution to that is to apply the inverse of the overweight. So the inverse of the overweight, it can be shown that the density, the extra weight depends or falls off as 1 over frequency. So the opposite of that is just to multiply by the frequency. Okay, so let's see the same idea now in 3D. So this is the central slice theorem. So we have an object, perform its projection. This is done by the microscope, and then we take the 2D Fourier transform, place it in the right position. Because we have many projections, we place all the many slices, and then once we have them placed in the correct position, we can apply a 3D inverse Fourier transform. And here is this idea that the overweight of the low frequency components decay as 1 over frequency. So the filter that we have to apply to the images is in principle, if we have a perfectly uniform distribution of projections, that would be omega. So this 1 over omega, or 1 over frequency, is derived under the assumption of a perfectly uniform distribution of projections. So there are no directions in which we have more projections than in other directions. And if this is not the case, for instance, there are some directions that are missing, or there are gaps between directions, then you should compute what is the weight. And for instance, this paper in CryoEM, it was one of the first deriving how to compute the filter for the weighted back projection for a specific geometries. And when computing the filter is a 3D function or a 2D function, depends on whether you're going from 1D to 2D or 2D to 3D. So and during the construction, you have to apply different gains or different windows, and then here you have the shape for different windows. So the one that is this straight line is the ideal situation in which you have perfectly uniformly distributed projections. So we have this the same idea in 2D or 2D projections are going to 3D. So the central region are overweighted because we measure them more often, and then there are a number of algorithms that they are called Fourier gridding. So the idea is similar to weighted back projection, to measure somehow what is the weight of each one of the Fourier coefficients, but now instead of reasoning in terms of angular distribution and a filter that you have to apply to the 1D Fourier transform or the 2D Fourier transform, you think of it as a weight that you apply directly in 3D. And here you have the papers, the references for this Fourier gridding in CryoEM. And I would say this is currently the state of the art for single particle analysis. So all algorithms nowadays, I would say, they are reconstructing in single particle analysis using this Fourier gridding idea. And the reason is that it is extremely fast, and especially this is very important when you have a high number of particles, as it is the case now. But Fourier reconstruction or somehow weighted back projection. Weighted back projection used to be the standard, and it is still very much used in electron tomography. But so weighted back projection and Fourier reconstruction are not the only ones that are available. There is another family of algorithms. This is an extremely rich family of algorithms in terms of variance, and these are based on some algebraic formulation of the tomographic problem. Okay, so let's see some of the tomography limitations. So we are all used with this problem from high school, where you were given 3 projections, and from these 3 projections you were able to reconstruct an object. Why is it that we cannot do it now in with macromolecules? Because at high school, with only 3, we could reconstruct a full object. And the trick was that in high school we were making a lot of assumptions about the kind of objects that we were constructing. And let's see here some of these. And so, for instance, let's say that we have this object, and this object generates these projections, and these the projections are compatible with the ground truth, but it is also compatible with this object. So this object that has been computationally constructed is compatible as compatible with the projection as the original object. So we cannot distinguish only from these projections. We cannot distinguish which of the two originated these projections. The assumption that we were doing at high school was that our object was compact, but otherwise, so the compact object would be this one. But otherwise, this object is also compatible with our measurements. And this happens, and this is very visible in electron tomography. So in electron tomography, let's say that we have this 2D image, and we generate 1D projections. And from these 1D projections, we we make a 3D reconstruction, or a 2D reconstruction in this case. So if we use all projections from all possible orientations in steps of 2 degrees, then this is what we get. If we take steps of 5 degrees, this is what we get. And we start recognizing these stripes. These stripes we already know where they're coming from. And in electron tomography, it happens that you cannot tilt the object inside the microscope between -90 and 90 degrees. So you have to tilt a bit less. So let's go to typical tilts like -50-50, but let's go little by little. So if we take projections only from -80 to 80 degrees, so that means that part of these projections are missing, then the 3D reconstruction is almost not affected. So just 10 degrees here or 20 degrees here of missing information, it is not very visible. If you make now this wedge bigger, now you start to see an elongation along this direction and a blurring of the information along the vertical direction, the direction in which we don't have information. And the bigger this missing wedge is the bigger the deformation. And this you may recognize now what are the features that you normally see in electron tomography. And there are many other artifacts, and some of them have to do with the visible area. So when you are tilting, the rays are going through different paths of your object. So for instance, when you have a 0 degree projection, the part of the object that is illuminated is this one, but when you are tilting by 45 or 60 degrees, the part of the object that is illuminated is much bigger. And then this causes artifacts in the 3D reconstruction. The same happens, for instance, when you tilt, part of the object may go out of the visible area. So this part of the object that sometimes it is visible, sometimes it is not visible, causes also artifacts. And this paper here is a very good description of the geometrical artifacts that you may find in electron tomography. And here you have some figure from the paper. And what we see here is that depending on what are the limitations, you might have very different 3D reconstructions of the same object. And so you see the different artifacts that are superposed to the object that ideally you should be reconstructing. And all these artifacts are coming from these facts that part of the object is visible, part of the object is not visible as you tilt along the tilt series. Okay, so this is the other family that I mentioned before. So this is an algebraic interpretation of the 3D reconstruction problem, and again we will not enter now into the details. But here what we are formulating the problem is in so you start with the model formation model. So with the image formation model. So the image formation model says you have some measurements. Those are your projections, and these projections are obtained by taking an object that is the 3D volume and applying some operator. This operator is making the projection, and if necessary is applying also the CTF. So it depends on whether you are considering the CTF for the 3D reconstruction or not. And then there is some noise on top of this ideal projection. And then what I want is to find the volume x star that minimizes the difference between my projections, and so the experimental projections and the reprojections from the volume I'm reconstructing. So this is a least square problem, and then you have a lot of theory behind how to solve this least square problem in many different ways. So one of the most common ways is by making iterative projections, so iterative 3D iterative reconstruction. And yeah, so we will not enter into much of those details, but it is interesting to see at least a part of it. That is, for instance, this let us see it in when we have art. Okay, so let's I think the best way I have is this one. Okay, so the iterative reconstructions, they take a current reconstruction and they produce a new estimate of what the object looks like. And for doing that, it takes the experimental images. So those are the experimental images, and it takes the current reconstruction, makes the projection, computes the difference, and then this difference is placed back in the space of volume. So if you think of this is a 2D image or a set of 2D images, and then this set of 2D images have to place them back in the 3D space so that you can add it to a volume. So this operator here, it is coming from the ideal projector. So the ideal projector has some diagonal terms, and so this is the diagonal terms. So yeah, all this family of algorithms like art, seared, weighted back projection, etc., they all go on making different choices of what is the composition that you are using. And something also very interesting is that you can have something that is a relaxation factor. So this relaxation factor makes that this update that you are doing here, this update, you're not doing the full update, but just a half of it or a quarter of it. So this relaxation factor, there are some theorems, and depending on the formulation, this relaxation should be between 0 and 2. But it is convenient to think of it as some number between 0 and 1. If it is 0, you don't move. If it is 1, you take the full correction. So the correction comes, the word correction comes because there is a mismatch between the my reprojection of the current volume and the experimental images. So I want to correct the current guess of the object, so that next time the error between my reprojection and experimentally observed data is minimized. Okay, so this relaxation factor is something that has a lot of impact on the quality of the 3D reconstruction. And here, this was actually my first paper. So it was about let's say that you have many more projections from one direction. So nowadays this topic is again very popular because we are having a lot of troubles with overloaded directions because of the interaction of the sample with the water interface. And then let's say that you have projections from everywhere, but some direction is overloaded. And it was reported that in this situation you were having some elongation artifacts, and actually these artifacts, they were not seen in weighted back projection. So is it a problem of the SIRT? SIRT is simultaneously iterative reconstruction technique, or are these algebraic reconstruction technique? And so is it a problem of iterative algorithms that work in real space? And the answer is no. If you run for many iterations, you converge to the right structure, or alternatively, you may play a bit with the relaxation factor, so that with this same number of iterations you can have the correct 3D structure. So this relaxation factor in iterative algorithms is extremely important to define what is the convergence rate towards the right structure. And this is something that normally we don't play so much. So in electron tomography, this SIRT algorithm is still very much used, but we normally don't play with the relaxation factor. But we should be aware that changing the relaxation factor plays a role. And yeah, so we can skip all this. Actually, there is a very nice connection between SIRT and gradient descent. And gradient descent is this algorithm where you start at a given location. This is your initial volume, and then you iteratively move towards the minimum of the goal function that you want to minimize. And the goal function that we want to minimize for SIRT is this one that we already saw. It is the least squares solution of this reprojection error. So we want the volume projected and then being similar to the experimental images. And there are many variants of these iterative algorithms depending on what are the specific weights and what are the specific updates that you are taking. But all of them, at the end, you may think of each one of the pixels as defining an hyperplane in the volume space. So that actually what you are saying is the sum of all these voxels along this path is this value. So you can formulate that in this way. So this is the value that you have observed, so this is your pixel value, and this is somehow a very compact way of writing the sum of the volume along that path that gives rise to this pixel. So this is the equation of an hyperplane. So all these iterative algorithms, they can be thought of projecting, successively projecting the current guess of the volume onto some hyperplanes. Okay, and then you would have this kind of plots where this is the right structure, and then you are successively projecting your volume onto the different pixels, or the hyperplane defined by the different pixels, and then you would converge to the right structure. And we had a review very recently, a couple of years ago, 2018 I think, or 2017, on all these iterative algorithms. And there are also very nice connections with match and unmatched back projectors. So the projector, we understand what it is. It is the process of making the summation along some direction and applying the CTF, for instance. So this could be our projector A, but then for the back projection, it might be that correcting for the CTF it is difficult. So we don't correct for the CTF, we just correct for the projection. So from the collapse from 3D to 2D. So this iterative algorithm is called an unmatched iterative algorithm because the forward model includes projection plus CTF, while the backwards model, it only includes projection. And then there are very nice convergence theorems about what is the relationship that allows you to reconstruct faithfully, even if you are not correcting for some of the effects. And then there are also many considerations about the speed of convergence. So you might have convergence theorems, but they may be very slow to converge, and those the speed of convergence is related to the condition number of the A transpose A matrix, and well, many very interesting stuff. Okay, so some other algorithm that is very popular, maybe not so much in CryoEM, but certainly so in medical imaging, is conjugate gradient. So in conjugate gradient, we have a similar formulation of the problem and a similar iterative algorithm. So, but the difference is now that instead of using the columns of the matrix A, as we are doing in ART, or the rows of the matrix A, as we are doing in ART and SIFT, we are using some other directions. And these directions are called conjugate directions, and they are constructed very much following the same similar ingredients. So we recognize here the reprojection error, and this part of the update has the same structure as we had in SIRT and ART. But there is one advantage of this conjugate gradient, that is that the algorithm converges exactly in the number of steps defined by the number of voxels. So this is if you update after every voxel. So yeah. Okay, so yeah, so here you have the formulation of the conjugate gradient. It was actually proposed for electron tomography, this conjugate gradient algorithm, but I think it was performed in Fourier space, so not in real space, but the problem formulation is similar, but only now that you are working with Fourier coefficients rather than with real space coefficients. And again, all these families, they are very active, and you have many different variants, and some of them they are more known than others. And there is another interesting idea, that is, okay, so what if instead of just solving the least squares problem of the reprojection, I can add some a priori knowledge. So for instance, I know that my object that I'm reconstructing belongs to some set, and this set may be convex, like for instance the set of non-negative volumes, or the set of symmetric volumes, or volumes that are defined within a mask, and so on. So some of the sets are convex. Here you have a representation of what is a convex set, what is not a convex set. The formulation of a convex set is that if you have two volumes that belong to that convex set, the linear combination of those two volumes with alpha between 0 and 1, so the segment that goes from volume 1 to volume 2, is fully contained within the same set. So that happens, for instance, for non-negativity. So if you have two volumes that are non-negative, any linear combination of those two volumes is also non-negative, and the same for symmetry. So if you have a volume or two volumes that are symmetric, any linear combination of the two volumes is also symmetric with the same symmetry. And iterative algorithms are very well suited for considering this kind of extra constraints. And the reason is that on top of the iterative algorithm that makes the projections more consistent, so all this is just the seared update, on top of that you can project onto the set of convex sets, and you have to find some suitable projection. So for instance, a suitable projection for a non-negative 3D reconstruction of 3D non-negative set is to clip simply the negative values and you set them to 0. Or for a symmetric set, then what you do is you symmetrize your volume after making the 3D reconstruction update. And then if you are in this setup of constraint optimization, then you can explore a different branch of mathematics that is using instead of this gradient descent, there is something called subgradient descent, and well, you can be very creative about this. Superiorization was one algorithm that was proposed by Jairsen or Gabor Herman. For these people are very well known in iterative 3D reconstruction, and they have their contributions to CryoEM also. And then this superiorization is a way of incorporating a priori constraints. And also, for instance, here you have another flavor of this incorporation of extra constraints on the 3D reconstruction. One of the most common constraints is sparsity. So sparsity, probably this is much more important or much more common in medical imaging than in cryo-EM, but the same ideas would apply to cryo-EM, and actually they have been already applied, especially to electron tomography. In single particle analysis, it is not so important because you have so much data that at the end, this sparsity constraint that is adding some a priori knowledge about the kind of objects that you are reconstructing, they are not adding so much information. Okay, so these sparsity constraints, they are based on the p norms of the object being reconstructed, and the p norm is defined like this. So we are all familiar with the squared norm. So with the p equal 2 norm, that is the Euclidean norm, the standard Euclidean norm. But there are many other possibilities. So you may choose p equal 1, p equal 0.5, and actually what this norm is saying is that, for instance, I want to reconstruct a volume. So I want to reconstruct an x such that this x is made of very few coefficients in some space. So this space can be defined by the standard transformations like the wavelet transform, the Fourier transform, the discrete cosine transform, or they can be constructed with ad hoc dictionaries that are specifically built for this specific problem. And the idea is that you take very few wavelet coefficients to make your volume. And here we have a representation of that. So if, let's say, this is the famous cameraman image. So if you do the wavelet transform, you see that the energy is concentrated at very few locations. So most of the coefficients are almost zero. And just a few of them have energy. So that means that the amount of coefficients, this zero norm is just a count. So the count of coefficients different from zero is you're looking for a volume such that the count of coefficients different from zero is minimum. So, and that you still are able to fully reconstruct your image. And then you may work with a dual problem. So you may minimize the count of coefficients different from zero in some space, subject to the reprojection error being smaller than delta, or you can work with the dual, that is, minimize the reprojection error subject to that the count of coefficients is smaller than something. And then here you have a plethora of algorithms like orthogonal matching pursuit or matching pursuit or many other variants like lasso, iterative reweighted least squares. So you have many possibilities. And one of the most successful iterative minimizers is this alternate interaction method of multipliers, and again it has been proposed also for CryoEM. We don't have the reference here because when I prepared these slides a few years ago, the paper was not published, but we have now a paper with Michael Unser and myself, in which we apply ADMM to single particle reconstruction. And well, so let's skip all these. Well, the other thing is that you can have a maximum a posteriori 3D reconstructions, and this maximum a posteriori is a scheme in which you have you want to minimize the reprojection error, and you have also some prior about the kind of objects that you want to reconstruct. So this prior is formulated as a probability distribution function. So depending on what is the probability distribution of your prior, so for instance, let's say that you have a prior on this LS. So S is the object that you want to reconstruct, and then L is some transformation of that S. So the prior on LS may be Gaussian, maybe Laplace, maybe a student. So depending on what is your prior, then you're having a different regularization term. And then you have to find some proximal operator. This proximal operator makes the role of this projector onto a convex set, but now it is not a projector onto a convex set, but a projector onto something that is more likely in terms of this prior. And actually, these depending on what is your prior, you might have different point-wise or proximal operators. And these proximal operators, for instance, you may use, so these are the priors that we had before, and these are the proximal operators, and some of them you may already recognize. So, for instance, if we use this linear attenuation is related to a Gaussian prior. So this linear attenuator, what it is doing is simply multiplying the reconstructed volume and transform it to some space, like the wavelet space or something, multiplying it by a constant that is smaller than 1. And then you have soft threshold. This soft threshold, or let's see first this shrinkage function. The shrinkage, well, the soft threshold. The soft threshold is this one. So the soft threshold is one that small coefficients are set to 0, and then the large coefficients you keep them as they are minus some constant. And this is very much related to this Laplace, or this is the proximal operator for this Laplace prior, and it is, you may recognize here things like total variation and these kind of regularizers. And you can construct a smooth approximations to the soft threshold proximal operator. And well, so the idea is that you have your reconstruction, you follow the standard 3D reconstruction process in which you try to minimize the reprojection error, and then as you are iterating over the volumes, you remove part, or you transform part of your coefficients. And for instance, a possibility could be you take your volume, the recurrent gas, take the wavelet transform, then apply the proximal operator there, and then compute the inverse of the wavelet transform. And these schemes have been shown to converge to the right structure, and you will see now an application of this soft thresholding. For instance, ICON, that was an algorithm. It is a mixture between SIRT and this soft thresholding that was proposed for electron tomography by the group of Fei Sun. And so what you have here is this kind of formulation where you want to minimize the zero norm of the reconstructed object subject to some to the data consistency. So the reprojections of my volume have to be consistent with the experimental data, and you can see that the results are very successful. So this is the weighted back projection, and this is of some data. This is the icon reconstruction, and here you have some other examples where you have in weighted back projection we have these stripes coming out from the gold beads, and we now understand why, because we are having these stripes that are compatible with the measurements that we were mentioning at the beginning. But with icon, because I'm forcing the volume to have very few coefficients to represent these stripes, I need some extra coefficients in some space, in some wavelet space, or even the real space. And then if by applying the soft thresholding, I'm forcing among all the possible volumes that are compatible with these measurements, choose the one that has fewer coefficients. So now we can recognize, we can go back to our one of our previous slides, this one. So we were saying these two objects are equally compatible with the measurements. But now if I put the constraint that it has to the count of non-zero coefficients in some space, and this some space could be even real space if you want. So the count of non-zero coefficients have to be small, then I can choose between these two objects, and this one has a smaller count of non-zero coefficients than this one. So that is why it is so successful in removing stripes. And so here you have the effect of this soft resolving on subtomogram averaging. So you see that if you do the subtomogram averaging on volumes reconstructed with icon, you have typically better local resolution than if you do it with weighted bar projection. And there is another idea, that is to interleave 3D reconstruction steps with some projector steps, if you want, that projects your volume into a set of volumes that are that have some nice properties that you are looking for. And these nice properties could be, for instance, that they are smooth. So you alternate 3D reconstruction steps with denoising steps, and these denoising steps in this particular algorithm, in this particular paper, they used nonlinear diffusion, and then they were applying 3D reconstruction and then denoising, then 3D reconstruction, then denoising, and you iteratively go in that way. And again, they show that with this field that they have much better reconstructions and with much less artifacts. It is not that they fully remove the artifacts, but they have much smaller than weighted bar projection alone. And here you have more examples. So weighted bar projection and art field and so on. And there has been another suggestion, like from this group, and it is MBIR. That this MBIR is now you recognize all these ingredients that we have been talking about, proximal projectors. So this is the proximal operator that they are using, and we understand now what is more or less the setup. So it comes from a prior on the distribution, statistical distribution of the coefficients of the volume. And stochastic gradient descent has been one of the latest additions, and the idea is that you can apply any algorithm, 3D reconstruction algorithm that you like, but not on the full data set, but just on a subset of it. And it has been shown that it is very successful in getting away from local minima, and the idea actually is coming from the deep learning community, and there they have millions of parameters to optimize, and that is why they require these very robust algorithms that can find global minima, or at least good enough minima. And this is the algorithm that is behind CryoSpark, but some other packages have also adopted this idea that I don't need to work with 1 million images, but I can work with a small subset of them, and then iteratively update my volume. And something else that I would like to highlight is this parameter refinement that we are doing at the end. So all this polishing, the polishing is just refining the projector operator, if you want, the A that we had at the beginning. So or the A, or even the yeah, the A, but changing the B if you want. So the idea is that you may refine very accurately what is the defocus, what is the frame alignment. So frame alignment would be changing B, the defocus would be changing A, and then iteratively find better alignment of the frames and find better CTF defocus based on the current estimate. So it is estimating A and B at the same time as you are iterating. And also, for instance, this is another change on B, so on the experimental data. That is, since I have all the frames, and I may try to estimate what is the relative damage that each one of the frames for a particular particle or a micrograph at most is suffering. So those frames that have been more damaged, they will get a smaller score or a smaller weight. And all these ideas, they are very nicely illustrated in this paper of Alberto Bartesaghi. And talking about 3D reconstruction, again, this is talking about A now. So how to transform a volume into a set of images. And the idea here is that it is not just the plane projection that gives rise to this central slice theorem interpretation, but that the Fourier coefficients of the 2D image are located along a surface, and in this theory, this surface is a sphere. So they are not coming from a plane in the 3D Fourier space, but they are coming from a sphere from the 3D Fourier space. And then when I put them back, I don't have to put them back into the plane, but I have to put them back into the sphere. And this is this Ewald sphere correction. So to summarize this talk, I would say weighted projection was one of the easy algorithms, so easy, relatively easy. So it is very easy to understand, not so easy to implement maybe, but it was the traditional. At present it is not so much used, at least in single particle analysis. For electron tomography it is still used. And then in single particle analysis, the current standard is the Fourier reconstruction, Fourier gridding, where you have to, it is similar to weighted projection. The ideas behind are similar, but they are implemented in Fourier space and they are much faster. And iterative algorithms, they are the standard in electron tomography, and they also allow for incorporating many different priors, like membership of a convex set, some constraints, a priori constraints like non-negativity or symmetry or being defined within a mask. These constraints in single particle analysis, they don't apply so much because we have so much data. But if in electron tomography, they can make a role, maybe not the ones of symmetry and being defined inside the mask. But for instance, these iterative algorithms also allow priors, and we have seen like all these soft thresholding or all these proximal operators or iterative iteratively constraining the reconstruction to have some nice properties like being smooth or whatever, how they impact into the quality of the reconstructed map. So this would be all, and I hope you found it useful.